So this often happens. You got a new approach, and there was an old approach, and there's tension. And there's, in particular, this guy Norman Campbell, who is getting very irritated by this. He's a Nobel Prize-winning physicist, and he basically says, well, you know, this isn't measurement, and that's the base. That's the base of this class. Is it measurement? When is something measurement? That's a basic issue. So what Norman Campbell says is, you know, if you just add scores, like in an intelligence test, and you just, you know, you can't just declare these things to be measures. Measurement is a really specific thing. It has a very specific meaning, and it's not like, you know, you can reinvent this. Measurement essentially requires that you have a very specific process of assigning numbers, not just any process. You can't just go around and giving people numbers and call them measures. You know, that's not then you're stretching terminology here. And he says, well, measurement is a very specific thing. It is the result of a very specific kind of numerical assignment in such a way that each object is represented by a single number, and the sum of two of these numbers corresponds with an empirical combination of objects. So if you take two masses and you put them together in a Penn balance, and you concatenate, as they call it, these masses, and that is their joint mass is the sum of the original masses. And this is a beautiful idea, even if I may be not entirely on board with Campbell. It's a really beautiful idea. It's, this is called the representational theory of measurement, and everybody should know it. It is like, you know, you have the fugues of Bach, and you have the sunflowers of Van Gogh, and you have representational measurement theory. It's just one of the great products of human culture. But the downside of it is that it's very complicated. If you want to read about it, you get all kinds of set theory and difficult mathematics, and it goes way too far. So that's why I have a very basic way of explaining it, namely with this apparatus here. This is a balance scale, and also one of the great inventions of mankind. And what I want to do is explain the representational theory of measurement to you by showing you how you can construct a measurement scale out of nothing. And that's why it's called fundamental measurement theory. I'm not going to presuppose that I already have numerical assignments or that I already have numbers. Okay, so I'm gonna start from scratch. And what I want to do is create a measurement scale for mass or weight. And what I'm going to show to you, I took some clay for my kids. So people who have attended University of Amsterdam already know this trick, but pay attention again, because I've told it many times and still I learn new things every time. Okay, so what I want to do, and what I would like you to instruct me how to do, is I want to build a standard sequence. And a standard sequence is very simply, for instance, a meter stick with equal centimeter marks. That's a standard sequence. Another example of a standard sequence is a set of weights. Right? So 1 kilo, 2 kilo, 3 kilo, etc. That's what I want. This is step 2 actually. I have now 2 things, and they are equally heavy. Pay attention. Ta 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 ta, almost equally heavy. They're too big actually. This won't work. I'm going to do it with smaller things, otherwise all my clay will be gone before I'm halfway. Okay, so and then?
Because then you would have like
take another
whole
one.
and a half and a half and a half and a half.
Well, if you got more clay, you can also say put 2 of them
Exactly,
on one
exactly,
side.
yeah. Because otherwise, well, it's not exactly the same, but almost the same. Okay. So let's just to make clear what we're doing here. Maybe we want to sort of define a unit here, because that's why this is step 2. we are now actually already looking at the equivalence of two weights. So we need to define a unit. Does anybody have a, let's call this the unit. What shall we call it? One denny. Can I use this? One denny. One denny. Okay, so we've now looked at, we've taken an arbitrary, does it matter whether I've taken this or any other? No, it doesn't matter. It's arbitrary, okay? Unit is arbitrary, important point. So I've now looked at the equivalence actually of these two things. And that's actually all that that I need. I need equivalence and I need order. That's all I need. Okay, so now I've got two. And now? What will I do now? Exactly. Okay, so I've got equivalence. I've got order. This is heavier than this. And now, this is a very, very important thing. The thing that happens here is absolutely central in the history of science. And if this were not the case, if this were not possible, then you would not exist in the way that you exist now. This is called, what Willem also called, concatenation. Concatenation means that you put two things in together. Concatenate them. It's also what Joe Michel talks about. And now, I have to balance it, you said. Okay. So, here is my... So now I've got two pieces of my standard sequence. I've got a one denny piece and I've got a two denny piece. So how do I make the three denny piece? I'll put the red. Right. My children will not like the fact that I put the different colors in one thing, but whatever. So okay, now I've got three, and then I can make, how do I make four? So this is 1, 2, how do I do that?
2 yellows and a red.
2 yellows and a red, and it works, it works. It works, it always works. I give this class a lot, you follow this, right? Yeah. And it always works, it never lets me down. And that's funny, because, you know, psychometrics often lets me down. But physics has a, you can do it in a classroom, right? Okay, so now I'm making a standard sequence. I'm messing up the clay of my kids, but whatever, I'm making a standard sequence. Does it? And it works. Do you know that they make the scale unreliable on purpose? So the arms are a little bit like this. They do that on purpose, because if it becomes too reliable, or no, sorry, too precise, then it's the smallest, you can never balance them anymore, because the smallest. So this is my standard sequence. 5 dennies, 4 dennies, 3 dennies. So this is my 5 denny. Now I've created the standard sequence. The standard sequence, 1, 2, 3, 4, 5. And this is how you do it. This is, when I was a PhD student, I often wondered, why is it that some things like length and weight are observables? What makes them observables? Well, how come that we got this is what makes them observable. This is what makes the trust in the skills. The fact that you can actually concatenate combinations of weights and produce new ones to match them, and you're constantly testing the adequacy of your skill. By assigning numbers to these weights, I can also produce new hypotheses. So just for instance, I know that if I take 1 denny and 3 denny, yes, and I put them in a scale with 4 dennies, which they have not been in one scale before. They have not, but what will happen? They will balance each other. You look like this is trivial. It's not trivial. If it were not true, then we could not shoot rockets to the moon, we could not build computers, we would be stuck in our Bierenvellen. Okay, so there it goes. It's amazing. It's amazing. A direct test of the quantitative structure of mass, in this case, or weight, well, how you want to do it. That I can do in the classroom, and it works. Right? Physicists should always think I'm lucky, because even though my theories are complicated, the stuff that I study is remarkably simple. Because people don't do this. If I did this with people, you know, if this was a person, and I'd put him down, he would go like, "Oh, I've been there before, you know. Well, why do I have to do this again?" Or this one would think, "What does the investigator want me to do?" And this one thinks, "Would they think there's something wrong with me if I concatenate with the other piece?" Of course, that's what people do. So that's also immediately the difference. Okay. So this is the summary for if the microphone falls off. And my artistic skills. So yeah, this is roughly the structure. You give some attribute, some proper thing, the number 1, doesn't matter which one, it's arbitrary. And then you concatenate it, and you make a third that's as heavy, etc., 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 and then you get the number 5. And that gives you your standard sequence. And so this is the core idea that's here. The core idea of what's called representationalism is that the empirical relations map numeric relations. So the numbers are a mirror to a deep structure of reality. If you get shivers around on your spine, that's correct. This is almost like magic. And I also hope that it's maybe you hate physics, maybe you hate numbers. That happens, I know. Maybe you hate statistics. Maybe you think, well, I'm just gonna do this class and then forever forget about it. But I hope it also sort of shows you that this is something really beautiful. And something that's really, really interesting and also a deep thing that we, in a very important sense, don't have in psychology. And that's not to discredit psychology. It is to show that human properties and attributes are really complicated, much more complicated than these things over here. So you got to be careful in reasoning about them, and you should not be naive. Not be naive about the numbers that come out of IQ tests or personality tests. That doesn't mean you should discredit them, that you should say, oh, all of these things are nonsense. That's, you know, childish. It means that you should reason responsibly about them, and that you should be aware that there's an important difference between psychological quantities or test scores and these kinds of numerical assignments, regardless of what else you think about this. The representational theory of measurement. What is measurement? Measurement is. It's not negotiable, it's not even a definition, it's like a discovery. You can't just call everything measurement. Measurement is the representation of empirical properties by assigning numbers to objects where the relations between the numbers represent or mirror relations between the objects. And that is why we can use these numerical representations to build imaginary worlds before we build the actual system. So we can build an imaginary bridge and assess whether it will stand or fall by using these numerical representations. And if we decide it stands and we build it according to specifications accurately enough, like I did here, the hypothesis will pan out and the bridge will stand. Amazing.